For nearly 2 years, a specific category of object kept appearing in James Webb's deepest images, small, unnervingly red, and scattered through the early universe in numbers nobody had predicted. And for nearly 2 years, the astronomers finding them had no idea what they were actually looking at. Then, in a series of papers published across 2024 and into 2025, several independent research teams converged on the same startling explanation, one that had been quietly proposed early on and dismissed by some as too strange to be the real answer, until the evidence became too consistent to keep doubting. Pale blue drift. The objects themselves earned their nickname almost by accident, the way so many strange discoveries in astronomy end up with names considerably less dignified than the mystery they actually represent. Researchers combing through Webb's earliest deep-field images kept flagging small, compact sources, some barely resolved into anything with visible structure at all, distinguished mainly by an unusually steep, unusually consistent reddening in their light across Webb's different filters. Astronomers started calling them little red dots, informally at first, in conversations and internal working groups, and the name stuck so thoroughly that it now appears, without any apparent irony, in the titles of serious, peer-reviewed scientific papers. What made these objects worth taking seriously from the very beginning wasn't simply their color. Plenty of things in the universe appear red for entirely mundane reasons, dust absorbing and scattering shorter wavelengths of light more effectively than longer ones, or simple cosmological redshift, stretching a distant object's light toward longer wavelengths as the expanding universe carries it further and further from us. What made the little red dots genuinely puzzling was the specific combination of that reddening with two other properties that, together, didn't fit comfortably into any single, familiar category of astronomical object. First, they were compact, remarkably so, often unresolved even at the sharp resolution Webb's instruments provide, meaning whatever was producing their light was confined to an extraordinarily small physical region, especially given how much light some of them were putting out. Second, and more puzzling still, many of these objects appeared to be sitting at extreme cosmological distances, existing within the first billion years after the Big Bang, precisely the same early cosmic era where astronomers had already been finding those unexpectedly bright, unexpectedly massive early galaxies discussed on Another Evening Together, the ones that had already forced a serious reconsideration of how quickly galaxies could plausibly form and grow in the young universe. Put those two properties together, extraordinarily compact and yet extraordinarily luminous, existing at a moment in cosmic history when galaxies were supposedly still small, fragmentary, and just beginning to organize themselves, and you get an object that doesn't fit comfortably into either of the two most obvious categories astronomers might otherwise reach for. It was too bright and too red to be an ordinary, small early galaxy made up mostly of young stars, since stellar populations of that size and age simply shouldn't produce this much light this efficiently, concentrated into a region this small. And it initially seemed too numerous and too consistently found across independent surveys to easily dismiss as some kind of rare, one-off anomaly or instrumental artifact. The first serious proposal, raised almost as soon as the earliest little red dots were being cataloged, pointed toward something considerably more exotic than an ordinary young galaxy, an actively growing supermassive black hole, sitting at the center of whatever host structure these compact objects actually represented, its surrounding disk of infalling gas and dust, heated to extraordinary temperatures by the sheer gravitational energy of material spiraling inward, producing a small, intensely bright, and characteristically red glowing region known to astronomers as an active galactic nucleus, or AGN for short. This kind of active black hole system is well studied and well understood in the more nearby, more recent universe, where astronomers have observed thousands of examples over decades of research, and the basic physics involved, gas falling toward a black hole releasing enormous amounts of energy as it heats up and radiates away that energy before crossing the black hole's event horizon, was never in serious doubt as a real, physically possible phenomenon. What made this explanation genuinely startling, rather than simply a reasonable, expected finding, was the sheer scale and timing it implied if it turned out to be correct. Supermassive black holes, the kind capable of powering an active galactic nucleus bright enough to be detected across more than 13 billion light-years of cosmic distance, are not supposed to form quickly. The standard picture of black hole growth, built up over decades of careful study in the more nearby, more easily observed universe, suggests these objects typically start as much smaller black holes, remnants left behind by the collapse of massive dying stars, and then grow gradually, patiently, over hundreds of millions or billions of years, steadily accumulating mass as they consume surrounding gas and merge with other black holes along the way. Finding evidence of fully active, brightly glowing supermassive black holes already present within the universe's first several hundred million years would mean that at least some of these objects found some way to grow considerably faster than the standard, patient timeline allows, adding yet another entry to the growing list of ways the early universe appears to have moved faster and organized itself more efficiently than the models built before Webb's launch ever anticipated. Confirming that this AGN explanation was actually correct, rather than simply the most exciting available guess, required considerably more evidence than color and compactness alone could provide. And this is precisely where the story spent most of 2023 and into 2024, with different research teams gathering spectroscopic data, splitting the light from individual little red dots into its full range of wavelengths, searching for the specific, well-understood chemical and physical signatures that would distinguish a genuine active black hole from other, less exotic explanations that remained, at least initially, still on the table. One especially important signature astronomers looked for involves the behavior of hydrogen gas in the immediate vicinity of a suspected black hole. When gas orbits extremely close to a supermassive black hole, moving at enormous velocities under the influence of that black hole's intense gravity, the specific wavelengths of light emitted by hydrogen atoms within that gas become smeared out, broadened across a wider range of wavelengths than the same hydrogen emission would show in a calmer, less extreme environment, an effect directly related to the same Doppler shifting principle that changes the pitch of a passing ambulance siren, except here applied to the extraordinarily fast, chaotic motion of gas whipping around close to an active black hole rather than a vehicle moving down a street. This broadened hydrogen signature, when detected, serves as one of the clearest, most reliable fingerprints available for confirming that a given object genuinely contains actively accreting material spiraling toward a black hole, rather than simply a compact clump of unusually red, unusually concentrated starlight. Beginning in 2023 and accelerating through 2024, spectroscopic follow-up observations of individual little red dots, conducted using Webb's near-infrared spectrograph, began turning up exactly this signature, broadened hydrogen emission lines, in a genuinely significant fraction of the objects examined closely enough to check. This wasn't a single, isolated detection that skeptics could easily dismiss as a fluke or a measurement error. Multiple independent research teams, working with different specific samples of little red dots drawn from different deep field surveys, began reporting the same broadened hydrogen signature, again and again, a level of independent, cross-validated confirmation that carries considerable weight within a field that has, as we've discussed on other evenings together, learned real caution about accepting exciting results before they've survived exactly this kind of repeated, independent scrutiny. That confirmation, real and significant as it was, still left an important part of the puzzle genuinely unresolved, one that turned out to be arguably stranger than the initial black hole discovery itself. Astronomers estimating the mass of these newly confirmed black holes. using the same well-established techniques applied to active black holes in the more nearby, more thoroughly studied universe, kept arriving at figures that seemed disproportionately, almost uncomfortably large compared to the total mass of stars in whatever host galaxy structure appeared to surround them. In the more familiar, nearby universe, astronomers have established a fairly consistent, well-documented relationship between the mass of a galaxy's central supermassive black hole and the mass of stars in the surrounding galaxy itself, generally finding the black hole to represent a small fraction, often less than 1%, of the galaxy's total stellar mass. A relationship so consistent across thousands of studied galaxies that it's become one of the more reliable rules of thumb in modern galactic astronomy. Several of the little red dots studied closely enough to estimate both quantities appeared to violate this well-established relationship dramatically, with black hole mass estimates coming in at 10%, in some cases considerably more, of the total estimated stellar mass surrounding them. An imbalance so far outside the normal, established pattern that some researchers initially wondered whether the mass estimates themselves might simply be wrong, produced by some subtle systematic error in how astronomers were interpreting Webb's spectroscopic data for these genuinely unusual, genuinely extreme early universe objects. That specific tension, an active black hole apparently far too massive relative to its surrounding galaxy compared to everything astronomers had documented in the nearby universe, became one of the central puzzles occupying researchers throughout the following year, and it turned out to hold an important clue toward finally settling what these strange, small, extraordinarily red objects actually were, a clue that required looking not just at the black hole itself, but carefully, skeptically, at exactly what kind of host structure might actually be surrounding it. That host structure puzzle turned out to require questioning, something almost everyone studying these objects had, quite reasonably, assumed at the outset, that the black hole and its surrounding galaxy were two separate, distinguishable components, the way astronomers normally think about a supermassive black hole sitting at the center of an otherwise ordinary collection of stars stretching out around it. A small but increasingly influential group of researchers began proposing something considerably stranger, that in at least some of these little red dots, the entire object might not represent a black hole embedded within a normal galaxy at all, but something closer to a single, extraordinarily compact, extraordinarily massive structure in which the black hole and its immediate surrounding envelope of gas were so tightly bound together that trying to separate them into distinct galaxy and black hole components, the way astronomers routinely do for more nearby, more familiar systems, might be fundamentally misleading for these particular objects. This proposal picked up an informal, evocative nickname of its own within the research community, sometimes called a black hole star, a deliberately provocative term meant to capture the strangeness of an object that behaves, observationally, somewhere between a single, extraordinarily bright point source and a genuine, if extraordinarily compact, galactic structure. Under this model, rather than picturing a relatively small black hole sitting at the center of an already formed, relatively normal early galaxy, researchers proposed picturing something more like a dense, collapsing cloud of gas in the process of actively forming both a rapidly growing black hole at its center and a surrounding, still forming stellar population simultaneously, the entire structure wrapped in a thick, extended envelope of gas and dust dense enough to redden and partially obscure the light escaping from the intensely active core at its center. This thick, enveloping gas turned out to be genuinely important to understanding both the unusual reddening that gave these objects their nickname in the first place, and the puzzling black hole mass estimates that had seemed so wildly out of step with normal galaxy scaling relationships. If a significant portion of a little red dot's observed light is being absorbed and reddened by dense surrounding gas and dust, rather than reflecting the object's true, intrinsic color directly, then estimates of both the black hole's mass and the surrounding structure's total stellar mass, both of which rely on carefully interpreting the specific brightness and color of light actually received by Webb's instruments, could be systematically skewed in ways that might at least partially explain the apparently extreme imbalance astronomers kept measuring. Testing this specific idea required a particular kind of careful, technical detective work, disentangling exactly how much of a given little red dot's observed reddening came from genuine cosmological redshift, the ordinary stretching of light caused by the universe's own expansion, carrying these ancient photons across billions of years to reach us. How much came from the object's own, intrinsic physical properties as an actively accreting black hole system, and how much came specifically from dust and gas sitting directly along the line of sight, absorbing and reddening the light passing through it before it could ever escape toward Webb's waiting mirrors. Untangling these three separate contributions to a single observed color required detailed spectroscopic analysis across a wide range of wavelengths, examining not just where a little red dot's light peaked, but the precise, detailed shape of its entire spectrum, since dust absorption, cosmological redshift, and an object's own intrinsic emission properties each leave subtly different, distinguishable fingerprints across that full spectral shape once researchers know specifically what to look for. Detailed spectroscopic studies applying exactly this kind of careful analysis, published by several research groups working somewhat independently through late 2024 and into 2025, began converging on a genuinely important, genuinely clarifying conclusion. A meaningful portion of the little red dots examined this closely did show clear evidence of significant dust obscuration, consistent with light passing through a genuinely thick, extended envelope of gas and dust before reaching Webb's instruments, exactly the kind of environment the black hole star model had proposed. When researchers carefully corrected their mass estimates to account for this dust obscuration, properly modeling how much of the observed reddening came from dust rather than the object's own intrinsic properties, the previously extreme black hole to galaxy mass ratios came down considerably, in many cases falling back into a range that, while still often somewhat elevated compared to the typical relationship observed in the nearby universe, no longer represented the dramatic, almost physically implausible imbalance the earliest, less carefully corrected estimates had suggested. This finding mattered enormously, not because it made the little red dots any less genuinely remarkable or any less scientifically significant, but because it helped separate what appears to be a real, still worth exploring astrophysical puzzle, early black holes that do appear to be somewhat overmassive relative to their surrounding galaxies compared to later cosmic epochs, from what turned out to be, at least in part, an artifact of not yet properly accounting for dust when these objects were first being studied with the necessarily rushed, necessarily preliminary analysis that tends to accompany any genuinely new, genuinely surprising category of astronomical discovery. That distinction between a real underlying phenomenon and an analytical artifact inflating its apparent strangeness is precisely the kind of careful, patient refinement that characterizes how genuine scientific understanding actually develops over time, and it echoes a pattern we've touched on across several other evenings together, exciting early results gradually being tested, refined, and in some cases partially walked back, not because the original discovery wasn't real, but because the full, accurate picture of exactly how strange that discovery actually is takes considerably more careful, patient work to establish than the excitement of an initial announcement typically allows for. Resolving one puzzle, though, opened up a considerably deeper, considerably more interesting question that has come to occupy much of the field's attention since, one that reaches directly back into the black hole star hypothesis and asks whether that model's core proposal, that these objects might genuinely represent something structurally different from an ordinary black hole embedded in an ordinary galaxy, was pointing toward something physically real, rather than simply a useful conceptual bridge that helped researchers think through the dust collection problem. Several theoretical astrophysicists took up this question directly, working through the physics of exactly what would need to happen for a supermassive black hole to grow this large, this quickly, within the universe's first several hundred million years. A timeline that, as discussed on other evenings together regarding the broader mystery of surprisingly early, surprisingly massive structures in the young universe, remains genuinely difficult to explain using the standard patient picture of gradual black hole growth built up over decades of study in the more nearby, more slowly evolving universe. Ordinary black hole growth, limited by a physical ceiling called the Eddington limit, describing the maximum rate at which a black hole can typically consume surrounding matter before the radiation pressure generated by all that infalling material actually pushes additional matter away rather than allowing it to fall in, simply doesn't provide enough time, even starting from a reasonably large initial black hole seed, to reach the kind of masses inferred for some of these little red dots within the available cosmic timeframe. This has led researchers to seriously consider several possible ways a black hole might grow faster than the standard Eddington limited picture would normally allow. Some theoretical models propose that black holes in these extreme, gas-rich, extraordinarily dense early environments might be capable of sustained periods of super-Eddington accretion, briefly consuming matter considerably faster than the standard limit would typically permit, a possibility supported by some detailed computer simulations of gas flow under these specific extreme early universe conditions. Though it remains genuinely debated exactly how long such an accelerated growth phase could realistically be sustained before the black hole's own feedback effects, the same radiation pressure the Eddington limit describes would begin disrupting and pushing away the very gas supply it depends on to keep growing. An alternative, and in some ways even more speculative theoretical possibility, involves the initial seed itself, the very first, smallest black hole that later growth builds upon. If some fraction of the earliest black holes formed not through the standard pathway of a massive star collapsing at the end of its life, producing a seed black hole with a relatively modest initial mass, but instead through the direct, catastrophic collapse of an enormous, unusually massive cloud of primordial gas, skipping the intermediate stellar stage entirely. The resulting seed black hole could begin its growth already considerably more massive than the standard stellar collapse pathway would typically produce, giving it a substantial head start toward reaching the enormous masses inferred for at least some of the little red dots, without necessarily requiring any period of unusually fast, super-Eddington growth at all. These direct collapse black hole seeds remain, it's worth being honest, a genuinely theoretical proposal, one that researchers have modeled extensively using computer simulations of the specific, narrow physical conditions that would need to exist in the early universe for a gas cloud to collapse directly into a black hole rather than fragmenting first into a cluster of individual stars, the more typical outcome under most conditions. Finding direct observational evidence of this specific formation pathway, rather than simply demonstrating its theoretical plausibility, remains an active, ongoing area of research, one the little red dots themselves have become an increasingly important test case for, since their unusual properties, including that persistently elevated black hole to galaxy mass ratio even after careful dust correction, are exactly the kind of signature researchers would expect if at least some of these objects trace their origin back to an unusually massive initial seed, rather than a more standard, gradual growth history. This is precisely the state of understanding the field currently sits at, a genuinely significant, cross-validated confirmation that many little red dots do indeed harbor actively growing supermassive black holes, evidenced by the broadened hydrogen emission researchers have detected repeatedly across independent samples, combined with a genuinely more nuanced, more carefully corrected understanding of their apparent black hole to galaxy mass imbalance. One that acknowledges dust obscuration explains part of the puzzle while leaving open a genuinely interesting, genuinely unresolved remainder, pointing toward either unusually rapid early growth, an unusually massive initial black hole seed, or some combination of both, still requiring considerably more research and considerably more data from Webb's ongoing observations before the field can settle on a single, fully confident explanation. Understanding what these unusual objects actually mean for the broader story of how galaxies assembled themselves in the early universe requires stepping back from the specific puzzle of any single black hole's mass or growth rate, and considering something researchers have started calling the little red dot population problem, a question about sheer numbers that turns out to carry implications reaching well beyond the individual objects themselves. When Webb's deepest surveys are examined systematically, counting every little red dot candidate identified across each observed patch of sky, and extrapolating that count across the full, much larger volume of the early universe those small patches represent, the resulting estimate suggests these objects were, during a specific window in cosmic history, genuinely abundant, considerably more common than the population of actively growing supermassive black holes astronomers had expected to find based on models built before Webb's launch. Some analyses have suggested that little red dots could represent a meaningful fraction, in certain estimates approaching or even exceeding the number of more ordinary early galaxies found in the same surveys, an abundance that, if it holds up under continued scrutiny, would mean actively growing supermassive black holes were not the rare, exceptional objects earlier models assumed them to be during this particular early cosmic era, but instead represented a genuinely common, almost routine feature of galaxy assembly during the universe's first several hundred million years. This abundance matters enormously for a separate, considerably older cosmological puzzle that researchers have been working through for decades, one involving a process called reionization, describing a fundamental transformation the universe underwent sometime within its first billion years, when the neutral hydrogen gas that had filled essentially all of space, since shortly after the Big Bang was gradually stripped of its electrons, ionized by an enormous flood of high-energy ultraviolet radiation, transforming the universe from a state that would have appeared largely opaque to this kind of radiation into the considerably more transparent state astronomers observe when looking at the more nearby, more recent universe today. For decades, the leading explanation for what actually produced enough ultraviolet radiation to ionize the entire observable universe pointed toward the first generations of massive, extremely hot, extremely luminous stars, forming in large numbers within the earliest galaxies and collectively flooding the surrounding intergalactic medium with exactly the kind of high-energy radiation reionization requires. This stellar explanation remained the dominant, most widely supported model throughout most of the pre-Webb era, though it always carried a persistent, nagging difficulty, requiring early galaxies to be considerably more efficient at actually allowing that ultraviolet radiation to escape into the surrounding intergalactic medium than more detailed physical models of galaxy structure seem to comfortably predict. Since a meaningful fraction of any galaxy's own ultraviolet output tends to get absorbed by gas and dust within the galaxy itself before ever managing to escape outward, the unexpectedly large population of actively growing supermassive black holes that Webb's little red dot discoveries have revealed offers a genuinely compelling alternative, or at minimum, a significant additional contributor to this long-standing reionization puzzle. Active galactic nuclei, the general category of object powered by actively accreting supermassive black holes, are well known from decades of study in the more nearby universe. to be prolific producers of exactly the kind of high-energy ultraviolet and even more energetic X-ray radiation capable of ionizing surrounding hydrogen gas, often considerably more efficiently, in terms of radiation actually escaping into the surrounding intergalactic medium, than the light produced by ordinary stellar populations tends to be, since the compact, extraordinarily bright emission from an active black hole's immediate surroundings faces a somewhat different set of obstacles, escaping its host structure, than the more diffusely distributed light coming from stars scattered throughout an entire galaxy. Several research teams have begun building detailed calculations, attempting to estimate exactly how significant a contribution these newly discovered, unexpectedly numerous active black holes could actually make toward the total ultraviolet radiation budget required to reionize the entire early universe. And the results, while still genuinely preliminary and still actively debated, suggest the contribution could be substantial, potentially significant enough to meaningfully ease the long-standing tension between the standard stellar reionization model and the detailed physical difficulty of getting enough ultraviolet light to actually escape ordinary early galaxies. Some estimates suggest active black holes similar to those found among the little red dot population could plausibly account for a notable fraction, in certain calculations reaching a substantial minority, of the total ionizing radiation required, working alongside rather than entirely replacing the contribution from massive early stars. The two sources combining to more comfortably explain how the universe actually managed to complete this fundamental transformation within the timeframe astronomers have independently confirmed through other observational methods. This connection matters considerably beyond simply adding another data point to the little red dot story specifically. It represents exactly the kind of unexpected, genuinely significant link between two previously separate areas of cosmological research: the detailed physics of individual black hole growth on one hand, and the large-scale, universe-spanning process of reionization on the other, that tends to emerge only once a genuinely new category of astronomical object has been discovered and studied carefully enough to reveal connections nobody could have confidently predicted in advance. Researchers studying reionization, working largely independently from the astronomers who first began cataloging and studying little red dots for entirely separate reasons, have found themselves drawn directly into this story, recognizing that an accurate accounting of how the early universe transformed from opaque to transparent may require taking seriously a population of objects that, only a few years earlier, nobody studying reionization had any particular reason to think about at all. This unexpected connection extends further still, into a specific, previously puzzling observation that had bothered researchers studying the very last stages of reionization for years before Webb ever launched. Detailed measurements of exactly when and how reionization completed, drawn from studying the light of extremely distant quasars passing through the intervening intergalactic gas on its way toward Earth, had suggested that the process finished somewhat later and proceeded somewhat more unevenly, patchily completing in different regions of the universe at different times than the standard stellar reionization model comfortably predicted on its own. An additional, geographically clustered source of ionizing radiation, concentrated specifically around wherever these actively growing supermassive black holes happen to be forming in unusually large numbers, offers a genuinely plausible explanation for exactly this kind of patchy, uneven completion. Since regions of the early universe fortunate enough to host an unusually large concentration of little red dots would be expected to reionize somewhat earlier and somewhat more thoroughly than regions relying primarily on the more evenly, gradually distributed ionizing radiation coming from ordinary stellar populations alone. Testing this specific connection rigorously remains an active area of ongoing research, requiring astronomers to carefully map the specific locations of confirmed little red dots against independent measurements of exactly where and when reionization appears to have completed across different regions of the observable universe. A genuinely challenging observational task, given how faint and how difficult to precisely locate these objects remain even with Webb's extraordinary sensitivity. Several dedicated observing programs are currently underway specifically to gather the kind of larger, more comprehensive sample of confirmed little red dots this cross-referencing analysis would require, building toward what researchers hope will eventually become a considerably more complete, considerably more confident picture of exactly how significant a role these strange, extraordinarily red, extraordinarily compact objects actually played in transforming the early universe from an opaque, neutral hydrogen fog into the transparent, structured cosmos we observe stretching out around us tonight. Beyond their possible role in reionization, little red dots have also begun reshaping how astronomers think about a considerably more basic question: exactly how galaxies and their central supermassive black holes grow together over cosmic time. That well-established relationship discussed earlier, the consistent ratio between a galaxy's total stellar mass and the mass of its central black hole observed so reliably across thousands of galaxies in the nearby universe, was never fully understood as a matter of underlying physical cause, even before little red dots complicated the picture further. Astronomers have long debated exactly why this relationship exists at all, whether the black hole's growth somehow regulates and limits how much surrounding star formation a galaxy can sustain, its energetic feedback heating and dispersing gas that would otherwise collapse into new stars, or whether the relationship instead emerges more passively, both the black hole and its surrounding galaxy simply growing in tandem because they draw from the same underlying supply of infalling gas, without the black hole necessarily exerting any direct, active influence over its host galaxy's star formation at all. Little red dots, existing as they do at a moment in cosmic history when this relationship appears to be genuinely, measurably different, even after careful dust correction, from what the nearby universe displays, offer researchers a genuinely valuable natural laboratory for testing between these competing explanations directly. If black holes in this earliest cosmic era really did grow disproportionately ahead of their surrounding galaxies, briefly existing in an unusually black hole-dominated state before their host galaxies eventually caught up in stellar mass over the following billion years or so, it would suggest the black hole's own growth, rather than acting as a strict, continuous regulator keeping pace with its surrounding galaxy step by step, might instead sometimes run ahead temporarily with the broader, more familiar balance observed in the nearby universe only fully establishing itself gradually, over a longer stretch of cosmic time than researchers had previously assumed necessary. That possibility, an early universe where black holes briefly ran ahead of their host galaxies before a more familiar balance gradually reasserted itself, connects everything discussed across this entire evening into a single, coherent picture, one worth holding on to as we approach the close of this particular thread. Little red dots may represent a genuinely distinct, genuinely important early phase in how galaxies and their central black holes came into being together, a phase where the underlying physics allowed black holes an early head start, whether through direct collapse seeding, temporarily accelerated accretion, or some combination of both, before the slower, more patient process of ordinary star formation eventually caught up, gradually building the more familiar, more balanced relationship between black hole and galaxy that astronomers have spent decades carefully documenting throughout the more nearby, more thoroughly studied universe. That gradually reasserting balance, black holes and galaxies eventually settling into the more familiar relationship astronomers have documented so thoroughly throughout cosmic history since, brings this entire story back around to something worth sitting with directly: the sheer, genuine speed at which this particular scientific mystery has actually been solved, or at least brought into considerably sharper, considerably more confident focus. Compared to so many of the other open questions we've spent evenings exploring together, little red dots were first flagged as a genuinely puzzling, genuinely unexplained category of object only in 2022 and 2023, in the earliest months and years of Webb's operational life, when researchers were still working through the telescope's first deep field images and beginning to notice small, unusually red sources appearing again and again across independent surveys. Within roughly 2 to 3 years, spectroscopic follow-up had confirmed broadened hydrogen emission consistent with active black holes in a significant fraction of these objects. Careful dust-corrected mass estimates had substantially resolved the most extreme apparent violations of established black hole to galaxy scaling relationships, and researchers had begun seriously connecting this newly understood population to the decades-old puzzle of cosmic reionization, building genuinely productive bridges between previously separate corners of astrophysical research. That pace, a genuinely mysterious, genuinely unexplained population of objects moving from initial puzzlement to a considerably clearer, considerably more confident explanatory framework within just a few years, stands in real contrast to several of the other open questions explored across other evenings together. The Hubble tension, still genuinely unresolved after more than a decade of careful investigation. The CERN penguin decay anomaly, still sitting below the formal discovery threshold after over a decade of accumulating data. The deep, unresolved debate over Yellowstone's occasional unusual seismic swarms, still requiring careful, patient, ongoing monitoring without any confident final resolution in sight. Little red dots, by comparison, represent something closer to a genuine, if still not entirely complete, scientific success story, a strange, unexpected discovery that researchers have managed to substantially explain within a remarkably short window of time, precisely because the specific combination of tools available, Webb's extraordinary spectroscopic sensitivity, decades of well-established theory regarding active galactic nuclei built up through studying the more nearby universe, and a genuinely productive, rapidly collaborative international research community happen to align unusually well for this particular puzzle. It's worth being honest, in these final few minutes, that substantially explained does not mean completely, fully resolved, and it would be misleading to close this particular story pretending every remaining question has been settled. It's worth naming a few of the specific open threads researchers expect to keep pulling on over the coming years, because the trajectory of this research matters as much as its current, already substantial progress. Webb's ongoing observing schedule already includes dedicated survey time, specifically designed to catalog a considerably larger sample of little red dot candidates than currently exists, work that should meaningfully sharpen the population statistics researchers rely on when connecting these objects to reionization and to the broader story of early black hole growth. Spectroscopic follow-up continues as well, with researchers working to obtain the same broadened hydrogen confirmation signature for a larger fraction of candidates, since the current confirmed sample, while genuinely substantial and genuinely convincing, still represents only a portion of the full little red dot population identified through imaging alone. The precise mechanism behind these black holes apparently accelerated early growth, whether through sustained super-Eddington accretion, unusually massive direct collapse seeds, or some combination researchers haven't yet fully worked out, remains an active, genuinely contested area of ongoing theoretical and observational research. The exact contribution these objects made to cosmic reionization remains an estimate rather than a precisely confirmed figure, actively being refined as astronomers gather larger, more comprehensive samples and develop increasingly sophisticated methods for cross-referencing little red dot locations against independent measurements of when and where reionization actually completed. And the full population statistics, exactly how common these objects genuinely were throughout the early universe, and exactly how that population evolved and eventually transformed into the more familiar, better balanced black hole and galaxy relationships observed throughout the more recent, more thoroughly studied cosmos, continues to be refined as Webb accumulates additional years of deep field observations, each new survey adding meaningfully to what remains, even now, a genuinely still developing picture. What has changed, decisively and significantly, over the course of this particular scientific story is the fundamental shape of the mystery itself. There is a particular kind of satisfaction available in watching a genuine scientific mystery move this far, this quickly, toward a real, substantive explanation, one worth naming clearly before we let this story rest for the night. It doesn't happen often, and it doesn't happen automatically. It required a specific, fortunate alignment, an extraordinarily capable new instrument arriving at precisely the moment decades of prior research into active galactic nuclei, black hole growth physics, and cosmic reionization had already built up enough accumulated understanding to actually make sense of what that instrument was suddenly capable of showing researchers. Little red dots could have remained a genuine, unresolved mystery for considerably longer than they actually did, the way so many other open questions in astrophysics have. That they didn't reflects both remarkable luck in the specific nature of the discovery and remarkable, sustained effort from a genuinely large, genuinely collaborative international community of researchers, each one contributing a piece, a spectroscopic measurement here, a theoretical growth model there, a careful dust correction analysis somewhere else entirely, gradually assembling a coherent picture out of what had initially seemed like nothing more than an inexplicable smudge of red light. Little red dots are no longer simply an unexplained category of strange, unexpectedly red points of light scattered inexplicably across Webb's deepest images, a genuine puzzle with no clear explanatory framework at all. They have become, through several years of careful, patient, cross-validated research, a genuinely understood, if still actively studied, category of astrophysical object, actively growing supermassive black holes embedded within dense, gas-rich, dust-obscured early galactic structures, representing an important, previously unrecognized chapter in the story of how the earliest black holes and galaxies in the universe's history came into being together. Growing and evolving in ways considerably stranger and considerably more interesting than anyone studying the early universe had confidently predicted before Webb's launch finally gave astronomers the tools necessary to actually see, in this much detail, exactly what had been happening out there, quietly, patiently, for over 13 billion years. Thank you for spending this long, quiet evening with us here at Pale Blue Drift, tracing one of the more genuinely satisfying scientific mysteries of the past several years, from a strange, unexplained smudge of red light in Webb's earliest images, through years of careful spectroscopic confirmation and patient dust-corrected analysis, all the way to a genuinely deepened understanding of how the earliest black holes in the universe's history grew alongside the galaxies surrounding them, and how that early, unbalanced growth may have helped transform the entire observable universe from an opaque, neutral hydrogen fog into the clear, transparent cosmos we observe stretching out above us tonight. If careful, patient mysteries like this one, the kind that actually do find their way toward genuine resolution given enough time and enough careful, collaborative scientific effort, are the sort of thing that helps your own mind settle into something calm and hopeful before sleep, there will be more evenings like this one waiting for you, more distant discoveries, more patient investigations, more long, unhurried nights built for exactly this kind of stillness. For now, let the rest of tonight be simple. Somewhere in the deepest, faintest patches of sky Webb has ever managed to photograph, Small, extraordinarily red points of light continue sitting quietly in the data, their light having traveled for more than 13 billion years to finally reach a mirror built specifically to notice them, carrying within it the story of black holes and galaxies growing together, faster and stranger than anyone expected, in the universe's earliest, most urgent chapter. And down here, wherever you happen to be resting, your own breathing can settle into its own quiet, unhurried rhythm, needing no further resolution before sleep finally arrives. Sleep well,